All right, so in example 2, we're just asked to graph this function. It's a log function, but we have a little bit different input, and label the asymptotes and intercepts, and state the domain and range of the function. All right, so you probably remember from 108, you probably did some transformations on functions. You did reflections and translations and things like that, some compression and stretches, all of that stuff. Well, what we can do on this one, sometimes I just like to plot points instead of like relying on my memory to know what happens to a function when you do different things to it. I sometimes just like to plot some points just to verify. So I can just choose some x and y values. Okay, so I'm just going to make a little table, x and y. All right, but I want to choose convenient values for the input to the log. Okay, so I'm actually going to create another column here because the input to the log is 2 minus x. Okay, and I would like to choose input values that are easy to evaluate, right? I mean, I could use my calculator, but sometimes it's just easier to choose good values and then not have to even bother with your calculator. So what are good values that are easy to evaluate the log of? Well, 0 would be where the asymptote is, right? We know that when you take the log of 0, that's undefined, and so that would give you the spot where the asymptote is, right? I can't actually evaluate it, the log at 0, but that tells me where the asymptote is. 1, right? Because 10 to the 0 is 1, and any power of 10 really would be good values to evaluate. So let's just start with those. All right. So if 0 is my input to the log, but that's equal to 2 minus x, right? Then x would have to be 2, right? That x value of 2 gives me a 2 minus x that's 0, and the 2 minus x is the input to the log. So that is undefined. Okay, and so I know there's the asymptote there. Asymptote there, because I can't actually evaluate the log of 0. All right, so if the input to the log is 1, then what does x have to be? Well, 2 minus 1 would give me 1, so x would have to be 1. And so that gives me, if I take the log of basically 1, then I'm going to get 0, right? And then when the input to the logarithm is 10, right, then what does x have to be? X would have to be minus 8. All right, so when x is minus 8, then 2 minus a minus 8 would give me the 10, and the log of that would be 1. Okay, so that gives me some points to plot. So let's just graph that. All right, so I know I have an asymptote at x equals 2, right? So I'm just going to sort of draw that in. All right, so that's where my asymptote is. All right, and then when x is equal to 1, y is equal to 0. So I have this point right here. It's on my graph. And when x is equal to minus 8, I get 1. All right, so what does that look like? Let's connect the dots. All right, so there's kind of a sketchy sketch of what that graph looks like. All right, so what else we need to figure out? We need to label the asymptotes, which I did. I labeled the asymptote x equals 2. And we want to find the intercepts. All right, well, what intercepts are just when either y is equal to 0 or x is equal to 0. So when y equals 0, we get the x-intercept. So the x-intercept is just going to be 1, 0, right? Because we've already figured that out from the points that we graphed. Now, when x is equal to 0, that gives you the y-intercept, right? So the y-intercept, we're just going to put in 0 for x, and what do we get? put in 0 for x, and you get the natural log of 2, okay, which is approximately equal to 0, comma 0.69 if I want a decimal approximation. Of course, the natural log of 2 would be my exact answer. And the domain, okay, well, x is now less than 2. You can see that our graph, x is less than 2, right, because we have the asymptote at 2, right? If in interval notation, we could list that as minus infinity to 2. Now the range, okay, so that's all the output values, and you can see that basically you can get any real number. So the range is just going to be all real numbers. Okay, or we could actually list it in interval notation as minus infinity to infinity. Okay. All right, that takes care of our graphing example, and we'll move on to some applications.